Hey, here's a video that has a solutions, I guess, to the parts of the 2012 number 1. And this looks like it has to do with simple harmonic motion. So let's see, let's just kind of look through this. We've got a mass on a spring, so we're talking about a force equals negative kx and all the stuff that follows from that. There's its equilibrium position, there's its mass, so on and so on. That says a spring constant k, which is not given. Fixed wall, I presume it's frictionless. Alright, and they gave us a velocity here, or a graph of velocity versus time. And they want us to determine the equation of this, including numerical values for all constants. Alright, well, let's see. The equation for something like that, for velocity, velocity as a function of time is equal to, this looks like it's a negative sine graph. Okay, so we don't get to choose which one. That's like as if they started with cosine, which I think is what we did too, right? But anyway, you have to match, of course, what their graph is. So it's negative a omega sine omega t, right? Okay, now how do we find these things? Well, omega is equal to the square root of k over m, but we don't know the k there, and we do know that this period is equal to 2 pi over omega. I'm just writing down some relationships that we know here. So that means that omega would be equal to 2 pi over t. And I think it's pretty easy to see from the graph here what the period is, right? It looks like it repeats every 0.7 seconds. So that means that omega is equal to 2 pi over 0.7. So that's our omega. The amplitude, let's see, how shall we find that? I guess there's a couple of ways we could get that. We know that, I'm thinking we could just read it out of the graph here. It certainly looks like it's 1.8, that this whole thing is 1.8, right? So, say we're looking at the graph here, we have this would have to be a omega would have to equal 0.18, right? That's the amplitude of this sine graph. Now, don't get the amplitude here. That's the amplitude of the original position graph, right? So this right here is the actual amplitude of the curve we're looking at. So a omega would have to be 0.18, which means a is equal to 0.18 over this times 0.7 over 2 pi. All right, so let's put that in here. So we got negative a times omega, so that's negative 1.8 a omega, right, times the sine of omega t. You notice that the number that actually ended up here was that, right? It's the actual amplitude of this. Okay? That's basically, I mean, you can look at that as a pre-calc problem. It's a negative sine graph. It's got a period of 0.7 and an amplitude of 1.8. So that's basically where we are left there. All right, part B. Given that the equilibrium position is at x equals 0, Determine the equation x of t, including numerical values for all constants. Well, x of t is the antiderivative of this, right? Or, we also know that x of t is equal to a cosine omega t, right? Either way, whether you take the antiderivative of this or use this, that gives us x of t is equal to, we figured out what a was. I'll let you find the numerical value of this. Remember we found it here, times cosine of omega, which is 2 pi over 0.7 t. And notice that this is where it has maximum velocity, so yes, in fact, the antiderivative of this would be that sine function. Its equilibrium position is at x equals 0. That's what we need it to be, and it's released from rest at time 0, so there isn't any like plus c or anything. This really is our equation. All right, so that's testing out some of the equations that we have seen in this chapter. Part C, calculate the value of k. Well, that should be easy enough now because I know this, right? So we'll move on to a separate sheet here. Part C, I know that omega is equal to the square root of k over m, and omega, or in other words, I guess we could rewrite that as k is equal to omega squared times m, right? Squaring both sides and solving that. So that means k is equal to, let's see, reading off my other sheet, that was, oops, that's alpha, that's a, the amplitude, sorry. Omega is 2 pi over 0.7 squared times the mass of the block is 0.3, and that should give you your k. And I'll let you find the numerical value for that. So part D, actually I've got my calculator here. I don't know why I'm just being calculator lazy. That would be 2 pi over 0.7 squared times 0.3. That's about 24. K is equal to 24 newtons per meter. If you look at the rubric, there's more than one way to get that, but I think that's what we just did there is the easiest one, considering the work we already did. All right, part D. Experiment 2. The block and spring arrangement is now placed on a rough surface, so now we have friction, as shown below. The block is displaced so that the spring is compressed a distance d and then released from rest. Okay, so on the dots that represent the block, draw and label forces, not components, that act on the block when the spring is compressed a distance of d over 2. So that's like when it's here, right? When it's halfway back. And this is when it's halfway back and it's moving toward equilibrium. And they want us to draw all the forces. All right, well, there's gravity. There's the normal force. And then when it's moving this way, the spring at d over 2, the spring is still compressed. So the spring is pushing it this way. That's the spring force, right? It's still pushing until it gets to equilibrium, at which point it would be pulling. And then since it's moving this way, friction always opposes motion. Friction would be this way. So the force of friction would be like this. I guess it would have to be a little bit smaller, but they don't care about the lengths of these as much as they care about the correct directions and the right number of forces. And now, when it's here, the gravity, normal force, and the spring, that's a G, sorry, and the spring force are all the same. But now, when it's moving away from the equilibrium position, so it's moving that way, that means friction will also be this way. They like all your vectors to be coming right from the little dot here. Sometimes in class I think we might have put that on the end here. I'm not sure if they would accept that or not, or give full credit for that, but I think it's better to put it coming from the dot. So the only difference is that friction is acting opposite, in the opposite direction. All right, part E. Draw a sketch of velocity versus time in this case. Assume that there is a negligible change in the period and that the positive direction is still to the right. So let's see. The block in the spring arrangement is now placed in the reverse. The block is displaced at the spring. It's compressed at distance d and then released. And the positive direction is to the right. So that means it's going to start with a 0 velocity and then start accelerating this way, right? So it's going to start going up. Positive velocity. Okay, now the period is still 0.7, right? So let me just mark those out. 0.7, and so the next one would be here. What's the effect of friction? The effect of friction is that the amplitude of everything is going to get smaller. It's going to eventually slow down, and friction will take all the energy out of the system, and it will eventually stop. So here, let's see, where's half of my period here? So maybe it starts out with some like big velocity, but then the velocity is going to decrease, right? The amplitude is going to decrease. Sorry, I'm marking my halfway points here. So something like this. Something like that. The important features of this graph are that you got the velocity starting off going up into the positive because they compressed it and then released like that. So notice it's not like this one, right? In this one, it's stretched this way and then released, right? And in this one, they very specifically said it is compressed at distance d and then released. So there are a few points for this. You can look at the rubric, but I know one of them was assigned for just having the velocity going up like this to start. And then you have to have the period needs to be right? There is, assume that there is a negligible change. Oh, sorry. Negligible means we can ignore it, right? So it's basically assume that there's no change in the period, so that's right. We made it 0.7 again, and that the positive direction is to the right. So you just need this sort of like damping sine wave. All right?